Good morning all. Today we are going to see a very important topic, that is self-geometric mean distance and mutual geometric mean distance. We will begin with self-GMD. It is also represented as GMR, that is geometric mean radius. Usually it is represented by a symbol d suffix s. To get a clear idea about the GMR, we will take a look back to the derivation of inductance of a single phase two-way system. This derivation we have studied in the video session of transmission line parameters part 2. This is the inductance of conductor A in the case of a single phase two-way system when both the conductors of the single phase system are separated by a distance small d. This relation can be written in this form. Further, taking this e raised to 1 by 4 to the denominator side, we will be getting the relation as 2 into 10 raised to minus 7 natural log of d by r e raised to minus 1 by 4, and this r e raised to minus 1 by 4 is represented as r dash. Now coming back to our current slide, the same relation is indicated here. Instead of r dash we have used the symbol d suffix small s. This is actually the representation of self GMD or GMR. Now let's understand the meaning of self GMD. For that you have to consider a hollow conductor of hypothetical radius ds. Since the conductor is not a solid one, there will not be any internal flux linkage. Therefore, the inductance term will occur only due to the external flux linkage. So, for that particular hollow conductor of hypothetical radius ds, we can write the inductance term as nu0 by 2 pi natural log of d by ds. Suppose the value of this inductance is same as that of the inductance of solid conductor. The simplified form of inductance of single phase two-wire line is given here. So that inductance of the hypothetical radius ds bearing hollow conductor is same as that of this inductance. That is, this term has to be same as that of this term. It will be possible only when the value of ds is same as that of r dash, that is 0.7788 r. So we can easily say that GMR is the hypothetical radius of a hollow conductor which replaces the actual solid conductor of radius r, such that the self-inductance of both the hollow conductor as well as the solid conductor remains the same. From this relation of self-GMD or GMR, I can easily say that self-GMD of a conductor has a dependency on the shape as well as size of the conductor, and it does not has any dependency on the distance between the two conductors, which is represented by small d. From this relation you can very well see that this self-GMD's relation has no dependency with the term small d. Next we are going to see the definition of mutual GMD. Its definition is very much similar to that of self-GMD. It is actually a hypothetical mean distance between two conductors such that their inductance value remains the same as that of actual arrangement of conductors. In the case of single phase two-way system which we have seen just now, the mutual GMD is actually this numerator portion, that is small d. So we can very clearly say that the mutual GMD between two conductors is actually the distance between both of them. If you see the example of single phase two-way system, the mutual GMD is small d. Small d is actually the separation between both these conductors, or I can say small d is actually the center to center distance between both these conductors. The purpose of this self GMD and mutual GMD is actually to simplify the calculations of inductance side. You will be able to get a clear picture of it in the upcoming slides. Now we are going to see a composite system. Before we have seen that a single phase two-way system. In that case the single phase system was composed of just two conductors. But if you see here, in this case, each single phase line is composed of numerous subconductors. I have considered one single phase line as capital M and the other single phase line as capital N. If you see here, this single phase line alone is composed of numerous subconductors. All of them are connected in parallel. Similarly, the second line is also composed of numerous subconductors which are connected in parallel. Please note a small correction here. In this case, the M conductor is made up of numerous subconductors and the total number of subconductors in this is small m, so this has to be corrected as small m. Similarly, in this case, this conductor is made up of n subconductors, so this has to be indicated as small n. Please note this correction because the derivation is done accordingly. Okay, so now the system which is taken into consideration is a composite system. Each single phase line is made up of numerous strands, or I can say each single phase line is made up of numerous subconductors. So in this case, the conductor M is made up of m subconductors and conductor N is made up of n subconductors. So I can say the current through each strand of this conductor M is I by M, considering the total current which is flowing through all these strands is I. As you know, the second conductor is used as the return path. So the current which will be flowing through each of these strands will be minus I by small n, as there are altogether n subconductors. Now let's see the flux linkage of this subconductor A. It will have the flux linkage due to its own internal and external flux. In addition to that, it will be having the external flux linkage of this conductor, this conductor, this conductor, and this all conductors. So while writing the flux linkage of this conductor A, the current flowing through this subconductor is capital I by M. So the flux linkage due to its own internal and external flux linkage can be written as nu 0 by 2 pi I by M natural log of infinity by R dash. That R dash term is indicated here as dAA. Next is the external flux linkage due to this conductor small b. The distance between these two conductors is indicated as dAB. So definitely we can write the external flux linkage due to this conductor alone is nu 0 by 2 pi I by M natural log of infinity by dAB. Similarly, the external flux linkage due to conductor C can be written like that. We can write the external flux linkage of all conductors, that is all subconductors in this single line. As I told, there are m subconductors, so the last term will be natural log of infinity by dAm. dAm is actually the distance between these two subconductors. I have already mentioned the correction. This is actually small m and this is actually small n. Please keep that in your mind. So now we have obtained the flux linkage of conductor A due to its own internal flux, external flux, and external flux linkage due to other subconductors from the same line. As I told you, this conductor A will have external flux linkage due to this subconductors in conductor N also. So writing down the external flux linkage due to this subconductors, we will be writing the relation as minus nu 0 by 2 pi I by N. Why this minus came here is, this phase line is actually the return path, so definitely the current which will be flowing through this phase line will be minus I, and the current which will be flowing through all the subconductors will be minus I by N, as there are n subconductors in this single phase line. Since the current which is flowing through each of the subconductors is minus I by N, in this relation it comes negative here. So the external flux linkage due to this conductor A dash will be nu 0 by 2 pi, actually minus nu 0 by 2 pi I by N natural log of infinity by dAA dash. dAA dash is actually the distance between these two conductors, these two subconductors. Similarly, you will be able to write the external flux linkage due to this conductor B dash. Its term will be minus nu 0 by 2 pi I by N natural log of infinity by dAB dash. AB dash is actually the center to center distance between this subconductor and this subconductor. So similarly, you will be able to write with all the subconductors in the return path. So altogether there will be n terms inside this negative term. Further simplifying this expression using the logarithmic expressions, we will get the relation in this form. Next, to find the inductance of conductor A, you have to divide the total flux linkage of conductor A with the current flowing through that conductor. As we know, the current which is flowing through the subconductor A is I by M, and then simplifying it, we will be getting the relation like this. The terms I both in the numerator side and the denominator sides will get cancelled. In the same manner, I can write the inductance of conductor B also, considering the distances from conductor B to other conductors. This term dBB will be indicating its GMR. Like this, we will be able to write the expression for LC, LD up till LM. As phase line conductor M consists of small m subconductors, all the small m subconductors will be having inductance terms. Therefore, we will be able to write the inductance from LA till LM. The values of inductance of subconductors will not be same as these distances are different. That is, the value of LA is not equal to value of LB, which is not equal to value of LB. Therefore, the average inductance value of subconductor of M can be represented as LA plus LB plus up till LM divided by small m. This relation will give you the average inductance value of each subconductor of conductor M. In actual practice, this conductor M consists of M subconductors, small m subconductors which are connected in parallel. So if you know the inductance value of a single conductor, then the total inductance value can be easily find out by dividing the inductance of a single conductor by the total number of conductors, which is small m here. That particular relation is similar to the parallel connection of resistors. So we will be able to obtain the inductance of the total conductor M as the inductance of a single conductor. The inductance of a single conductor is obtained by taking the average value. So L average represents the inductor of single subconductor. This divided by total number of subconductors, that is M, will be giving you the total inductance of phase line M. So you have to divide this relation further by small m. Then the denominator term will be having M square. In this relation, the numerator term is actually the addition of this LA, LB till LM. So by taking 2m into 10 raised to minus 7 common from all the expressions and then using the logarithmic expression, we will be able to write the relation in this particular form. That is, natural log of A plus natural log of B can be written as natural log of A into B. That standard expression is being followed here, as there is a m square term in the denominator and there will be a m term in the numerator. That particular term in the numerator gets cancelled and we will be left with a small m at the denominator. If we are taking this particular term inside the natural log terms, then the whole term, both the numerator as well as denominator, has to be raised to 1 by m. Then we can write the expression like this. So this is the final relation for inductance of phase conductor. In this expression, the numerator is actually the mnth root of product of mn terms, whereas the denominator is actually the m squared root of product of m square terms. Please note a correction in this expression. This m term won't exist here, as we have taken this m term to the inside of this natural log term in the previous slide. So while comparing this expression with this particular expression, it's very clear that the numerator portion will be indicating the mutual GMD of this composite conductor and the denominator term will be indicating the self GMD or GMR of this composite conductor. That is, the denominator term can be indicated as D suffix small s, whereas numerator term can be indicated as D suffix small m. That is, this denominator term is actually the radius, that is the hypothetical radius of a hollow conductor giving the same inductance value as that of the composite system. Similarly, this denominator value will be giving a hypothetical mean distance having the inductance value same as that of the actual arrangement of conductors in the composite system. So that is the explanation for self GMD and mutual GMD in this composite conductor system. You don't need to by heart this relation. You just need to understand the logic, how to write this expression. Then it's very easy to write it down. Next we are moving to three-phase double circuit lines. Usually the three-phase transmission lines are working with more than one circuits in parallel. In this case, if you analyze, This three-phase system consists of two circuits per phase. If you are considering phase A, it consists of two circuits, that is conductor A and conductor A dash. Similarly, if you are considering phase B, it also consists of two circuits. Similarly, phase C is also consisting of two circuits. Therefore, we are saying it as three-phase double circuit lines. The main aim to provide more than one circuits in parallel is to get a low inductance value. As you all know from the standard expression for inductance that inductance term is having a dependency on both self GMD as well as mutual GMD. So a low inductance value can be easily achieved by having a high value of self GMD and a low value of mutual GMD. In order to achieve this large value of self GMD and a low value of mutual GMD, individual conductors of a phase, if you can see here, this is actually two conductors of phase A. They are separated as widely as possible. If you see this case also, you will be able to see these two conductors are placed as widely as possible. So definitely their DS value, that is self GMD value, will be very large. And to achieve a low value of DM, that is mutual GMD, the distance between phases are kept very small. You will be able to see the distance between this phase conductor A and phase conductor C and phase conductor B. All these distances are very small comparing with the distance of individual conductors of a particular phase. So by keeping the individual conductors of a particular phase as far as possible, we will be able to achieve a large value of self GMD, and by placing the phase conductors as near as possible, we will be able to achieve a very small value for the mutual GMD. Thus, by providing more than one circuit in parallel in the three-phase system, we can easily achieve a very low value of inductance by placing the individual conductors of a phase as far as possible and the distance between phase conductors as near as possible. Now let's calculate the self GMD and mutual GMD in this case, that is three-phase double circuit lines. The self GMD of phase A can be found out by calculating the m squared root of the product of m square terms. In our case, or in this particular case, the value of m is 2. So definitely the m squared root will be fourth root of the product of this four distances, that is the distance between this conductor A and A dash and the distance between conductor A dash and A. Then R dash value of this conductor, considering the radius of this conductor as R. Then this dA will be indicating its R dash value. Similarly, R dash value of this conductor, which is represented as dA dash A dash. Similarly, we can write the self GMD of the other two combinations also, that is of phase conductors B and of phase conductors C. As the distance between these phase conductors are not equal, we can say that this is actually an unsymmetrical arrangement. So definitely there will be transposition. Hence the equivalent self GMD of a particular phase can be obtained by taking the cube root of the product of this three. It is indicated here. Next we are going to find out the mutual GMD between phase A and B. From this arrangement, it's very clear that phase A consists of two conductors and phase B is also consisting of two conductors. As we know, the standard relation of mutual GMD is the mnth root of the product of mn terms. So in this case, the value of m and n is 2. So the value of mn will be 4. That's why we are getting the fourth root of the product of 4 terms. The 4 terms will be the distance between A to B dash, A dash to B and A dash to B dash. Similarly, we can obtain the mutual GMD between phase B and phase C. In the same manner, we can get the mutual GMD between phase C and phase A. As the conductors placed here are in unsymmetrical arrangement, so definitely the principle of transposition will be coming into effect. Therefore, the equivalent mutual GMD can be calculated by taking the cube root of the product of these three terms. From this relation, it's very clear that this mutual GMD term has dependency only on the spacing, and it is independent of the shape, size and orientation of the conductors. Hopefully the concept of self-GMD and mutual GMD is clear for you. Next we are going to see some problems. In this first problem, the arrangement given is actually a double circuit single phase line. You will be able to see that very clearly here. It's actually a single phase. Basically the single phase system will consist of two conductors. So in this case, each conductor is further made up of two subconductors, A dash and B dash. So it's actually a single phase double circuit arrangement. The radius of the conductor and the spacing is clearly given. You are asked to find the inductance per kilometer of the resulting double circuit line. Please note that you are asked to find the inductance per kilometer. In this problem, you have to find the value of ds and dm first. The value of ds, that is the self GMD, can be calculated by using the expression fourth root of the product of four terms, and that four terms will be daa, da dash a dash, then daa dash and da dash a. Similarly, you have to find the mutual GMD dm also. That is actually the mnth root of the product of mn terms, but in our case the value of m and n is same, so you have to find the fourth root of the product of four distances. That is the four distances are dab, dab dash, then da dash b dash and a dash b. Then you will be getting the value of mutual GMD also. Thereafter you can use the standard relation for inductance per conductor per meter, that is 2 into 10 raised to minus 7 natural log of dm by ds. After making the suitable substitutions of dm and ds, you will be getting the value of inductance per conductor per meter. But you are asked to find the inductance per kilometer of the resulting double circuit line. So the inductance per kilometer can be easily found out by multiplying the inductance per meter with 1000. Since you are asked to find the inductance per kilometer of resulting double circuit line, you have to find the value of loop inductance, which can be calculated by multiplying this inductance per conductor per kilometer into 2. You have to solve this problem by yourself and send to me. Similarly, if you are considering this problem, this is actually a three-phase double circuit line. The conductor radius is given as 1.3 centimeter, and this distance is given 3 meter, and this distance is 6 meter. See, in this problem you might have a doubt how you will calculate the value of this distance. It's very easy because this is actually a right angle triangle. Similarly, here also you can calculate the value of this distance by using the hypotenuse theorem. In this case, in order to calculate the value of self GMD, you have to find the values of ds1, ds2, ds3. Then you have to take the cube root of product of these three terms. Then you will be getting the value of ds. Similarly, in order to get the value of mutual GMD, you have to find the values of DAB, DBC and DCA, and then you have to take the cube root of product of these three terms. Then you will be getting the value of DM. Then you have to calculate the value of inductance per meter per conductor. Then further multiplying it with the 1000, you will be getting the value of inductance per phase per kilometer. You are not asked to find the loop inductance in this case, so you don't have to multiply it with 2, you are just simply asked to find the inductance per phase per kilometer. In this case it is clearly asked to find the resulting inductance per kilometer of the resulting double circuit line. So in today's session we have discussed in detail about the self GMD and mutual GMD. We had started with the definition of self GMD and mutual GMD. Then we have considered the composite conductor system and we obtained its inductance derivation. Then we have seen a three-phase double circuit system. There I very well explained the purpose of double circuit lines rather than single circuit one, and why these conductors are placed like this, that is also clearly explained. In order to reduce the value of inductance, the value of ds has to be increased and the value of dm has to be reduced. In order to achieve this, we are making this particular arrangement. Finally, we have discussed two numerical problems associated with it. This is a very important topic. You have to get the logic of this, then only you will be able to solve the problems associated with this. In order to get a better understanding of this topic, try to watch this video session more than once, and if you are having any doubts, we can discuss it during our Google Meet session. Thank you.